Good afternoon everyone. I am Dr. G. Seshadri, working as a Associate Professor, Institute of Aeronautical Engineering, Department of EEE. So today I want to discuss about analysis of electrical networks. In these networks topics, I want to discuss about the behavior of pure resistor, inductor and capacitor. In these three resistance, inductance and capacitance are the three parameters of electrical networks. And I want to discuss about the behavior of electrical circuits when AC supply is given to these three parameters. So first of all, I want to discuss about the alternating current through a pure ohmic resistance. So we know what is meant by resistance. It is the opposition of electrical flow of electrical current in a conductor. The resistance units are ohms, and when an AC supply is given to a pure resistance or pure resistor, then the instantaneous value of current will flow when an AC voltage is applied. So according to the equation, alternating voltage equation, so it is nothing but V of t at the instantaneous time t equal to maximum voltage into sin theta. Also theta is nothing but omega t, theta equal to omega t angular velocity into time. So let us say R equal to ohmic resistance in ohms, and I means I of t is the instantaneous value of current, and in this a pure resistor means the applied voltage must supply the ohmic voltage drop only. So in a pure resistor, whatever the voltage is applied, you have to compensate the voltage drops in the circuit. So in this, for equilibrium condition, V of t equal to I of t into R. It is nothing but ohmic drop. When the current flowing through a resistor, that is instantaneous current flowing through a resistor, the ohmic drop, that means I into R is nothing but drop. The ohmic drop will be there. I'm putting the value of V of t from the above equation. V of t is nothing but Vm sin omega t. So V of t is Vm sin omega t. So V of replacing Vm sin omega t here, and I of t into R. But according to Ohm's law, the current I of t is nothing but Vm sin omega t by R. I equal to V by R. Here in AC circuit, I is I of t, V is V of t at instantaneous value. These are the instantaneous values. So that is nothing but Im sin omega t. This is equation number 2. Equation number 1 is the V of t equal to Vm sin theta or Vm sin omega t, and equation 2 is the I of t, or is nothing but Im sin omega t. The behavior. So hence the voltage applying is a sine wave. Sorry, that is alternating voltage. With respect to time, the quantity also varies alternatively. It starts at 0 and reaches maximum at pi by 4 and reaches to 0 at pi, and again in the reverse direction in half cycle, negative half cycle, it starts increasing and reaches maximum value here, and again it reaches to 0 at 2 pi. So these are in x-axis we are taking time t in seconds, and in y-axis we are taking the quantity whatever it may be. Here I am taking v of t, and another it follows I of t. So in a pure resistor, both these are irrespective of the amplitude and magnitude. It starts at the same time and reaches maximum at the same time, and again reversal happening at same instantaneous value. So these two are said to be in same phase. These two are said to be in same phase. So if it is v of t, I of t also follows the same phase. So for a pure resistor, we can say that the behavior of voltage and currents both are in the same phase. There is no any phase angle difference between the two quantities. Hence the current I is maximum. We know that from this equation at theta equal to 90, the sin omega t is unity. So when sin omega t is unity, Im equal to Vm by R. Sin theta is unity. So Vm by R. From equation 2, we are applying sin theta value as unity, and Im equal to Vm by R. So equation 2 becomes I of t equal to Im sin omega t. Here the applied voltage symbol for applied voltage V equal to Vm sin omega t, and when we connected this to a resistive circuit, the current I will flows here. The current I will flows. When the current is flowing through a resistor, definitely there is a voltage drop which is nothing but VR. And we will take one problem for this. A 60 Hz voltage of 115 volts RMS value is impressed on a 100 ohm resistance. So here for 100 ohms resistance circuit, we are applying a single phase AC supply, that is 50 Hz, 115 volts. We need to find out write the time equations for the voltage and the resulting current. Let the 0 point of the voltage wave be at t equal to 0. So we need to find out at the 0 instantaneous value at time t equal to 0 seconds. So solution. Before going to solve this problem, first we need to understand the problem. Here if supply frequency is given, that is 60 Hz supply, and a voltage 115 volts RMS value, this is giving to the 100 ohms resistance. So we need to write the time equations for voltage and current. Okay. So from this we can understand that we know the RMS value is given 115 volts. We need to find out the maximum value. So Vmax is nothing but root 2 times of Vrms. So here we are applying RMS value root 2 into given RMS value as 115 volts. So root 2 into 115 will get 163 volts first Vmax. After finding maximum value of voltage, immediately we can find, as the resistance is given, we can find out according to Ohm's law, Imax. The formula for Imax is Imax equal to Vmax by R. V by R. So Vmax we already find out 163 volts, and by R is nothing but 100. So again 1.63 amps. And already given at 0 point of voltage, we need to find out the value, that is at theta equal to 0. Theta equal to 0. And angular velocity omega equal to 2 into pi into f. So again 2, pi value 3.14. And again f, here the supply frequency is given as 60. So 2 into 60 hertz, pi into 60. So 120 pi. 120 pi. Also it is nothing but 377 radians per second. Angular velocity units are radians per second. Next, the required equations. So ask for the time equations for the voltage and current. So now we can apply the Vm and Im values. So we can write the V of t and I of t. So V of t, Vm sin omega t. Already omega t value is given. Omega value we know that. And Vm value 163 volts. And Vm sin omega value 377 radians per second into time. And I of t, similarly I of t, Im value we know Im is 1.63 amps, and I of t is nothing but 1.63 sin 377 t. And now we will see the behavior of pure inductor when an AC supply is given. So whenever an alternating voltage is applied to a pure inductive coil, a back EMF or counter EMF is produced due to the self-inductance of the coil. So at every step the back EMF opposes the rise of fall of current through the coil. As there is no any ohmic voltage drop, the applied voltage has to overcome the self-induced EMF only. So it has to supply the self-induced EMF only. So self-induced EMF according to voltage expression V equal to L di by dt. So L is the inductance in henries and di by dt is the rate of change of current in that inductor. So we know V equal to Vm sin omega t, and therefore we are applying V value in first equation. Let's say equation number 1, equation number 2. So Vm sin omega t equal to L di by dt. From that di is nothing but Vm by L into sin omega t dt. So this is the symbol for inductance. And when an AC supply is given to the inductor, it starts the current flowing through this inductor. So in this pure inductor, the current lags the supply voltage exactly by 90 degrees. So for this current equation, I equal to dI equal to Vm by L sin omega t dt. And when integrating on both sides, it becomes I equal to Vm by L integral sin omega t dt. But integral of sin omega t is nothing but cos omega t. And Again, cos omega t by omega, it becomes Vm by omega L. I equal to Vm by omega L into sin omega t minus 90 or pi by 2. So, I is maximum when sin omega t minus 90 is equal to 1. And I am equal to Vm by omega L and I equal to Im sin omega t minus pi by 2. So, I equal to Im sin omega t minus pi by 2. It means the current lags the applied voltage by exactly 90 degrees. Minus means lagging. Plus means leading. So, it lags the applied voltage by 90 degrees. And therefore, V equal to Vm sin omega t and I am equal to Vm by omega L, that is I equal to Im sin omega t minus pi by 2. So, let us say this is the applied voltage and after 90 degrees or after pi by 2 radians, the current starts conducting, and after 90 degrees the current reaches to the end of the positive half cycle and starts conducting in negative half cycle. Exactly after completion of voltage after 90 degrees or after pi by 2 radians, it comes to 0. It means the phase angle, that phase difference between this voltage and current is exactly 90 degrees in pure resistor. So from these equations we can say that the current lags exactly 90 degrees behind the voltage, and I am equal to Vm by omega L, that is Vm by omega is nothing but again 2 pi f, omega is 2 pi f, 2 pi f again it is nothing but inductive reactance. So we can say that I am equal to Vm by omega L or x suffix L, or from this x equal to xl equal to Vm by Im. It is also called inductive reactance and the units are ohms, where xl is the inductive reactance and units are ohms. So we can say that this xl directly depends on the frequency of the voltage. Higher the frequency, higher the inductive reactance, and vice versa. We will see another problem. A 60 Hz voltage of 230 volts, effective value is impressed on an inductance of 0.265 henries. Write the time equation for the voltage and the resulting current. So we need to write the V of t and I of t. We know the RMS value is given is 230 volts and we know Vm equal to 2 into Vrms. So RMS value by maximum value equal to 1 by root 2. So from this we can find out the Vmax value. Root 2V equal to root 2 into RMS value 230. Also angular velocity, angular frequency omega equal to 2 pi f. So it is frequency is given 360 Hz, 2 into pi into f60, that is 120 pi, that is already found first numerical problem. It is 377 radians per second. Now in this problem we need to calculate the XL value. XL equal to 2 pi f or omega L. So omega already calculated, that is 377 into L value. L value is given 0.265 and this. So after substituting, XL value is 100 ohms. And again Vm by Im equal to XL. So it is directly proportional to XL will directly proportional to the Vm value. If Vm is high, XL is high. So Im is nothing but Vm, that is root 2 into 230 divided by XL. XL is 100. So you got root 2 into 2 point. The time equation for voltage now we can write V of t equal to Vm sin omega t. Vm is 230 root 2 into sin omega is 377 to time. Voltage equation. And current equation is I of t equal to Im sin omega t, but omega t minus pi by 2. It is since it is a pure inductor, it lags by 90 degrees. So Im is 2.3 root 2 sin omega t 377 t minus pi by 2 or minus 90 degrees. Now AC through pure capacitor. Whenever an alternating voltage is given to a pure capacitor or capacitor circuit, so we will see the behavior of the current and voltage in capacitor circuit. So here V of t is giving, applying alternating voltage. V of t, Vm sin omega t is giving. Immediately after supplying the current, instantaneous current I will flow through the circuit. So because of capacitor reactance, there will be a drop I into Xc, nothing but voltage drop in pure capacitor. So the expression for current is I of t equal to C dV by dt, C dV of t by dt. Rate of change of voltage, inductor, rate of change of current, in pure capacitor, rate of change of voltage. So d by dt of V of t, here V of t is again Vm sin omega t, derivative of Vm sin omega t is cos omega t into omega. So C omega Vm cos omega t. But Im is Vm by 1 by omega c, where Xc is the 1 by omega c. Omega is again 2 pi f. Vm by Im is Xc. Also 1 by omega c is 1 by 2 pi fc, where X is called capacitor reactance in ohms. Therefore, V equal to Vm sin omega t, and also I equal to Im equal to Vm by omega L, and I equal to here Im sin omega t plus pi by 2. So plus for leading. It means that it is the voltage, supply voltage, and it is the current. So applied current will starts 90 degrees before the current, starting of current. So it is the behavior of response. It is current. So exactly there is a phase difference of 90. So from these two equations, we see that the current leads the voltage by exactly 90 degrees. We will see a numerical problem for this capacitor circuit also. Here, a 50 microfarads capacitor. The units for capacitance is farads, microfarads, and units for capacitor reactance is ohms. A 50 microfarads capacitor is connected across a 230 volts supply. 50 hertz, 230 volts, 50 hertz supply. Calculate A. Reactance offered by the capacitor. Reactance, that is Xc. B. The maximum current Im, and the RMS value of the current drawn by the capacitor. We need to calculate the root mean square value or effective value of the current drawn by the capacitor. Okay. So first we need to calculate the value of capacitor reactance. For this we need capacitor reactance X equal to Vm by M or 1 by 2 pi fc. Omega equal to 2 pi f. Already frequency is given as 50 Hz supply. 2 into pi value 3.142 into 50. 100 into 3.14. 314.14 radians per second. And Vm, maximum value is the root 2 times of the effective value. So from this we can find out the root 2 into 230 is nothing but maximum value. And X equal to 1 by omega c, that is 1 by omega value 314, round figure, into 50 fc. 50 microfarads. Micro is nothing but 10 power minus 6. 50 into 10 power minus 6 farads is nothing but 63.6 ohms. The value of X is nothing but 63.6 ohms. And V by I is nothing but Xc, or I equal to V by Xc. So V is given 230 and Xc I have calculated as 63.6 ohms, and we can calculate I equal to 3.62 amps. And Im is nothing but root 2 into I. Root 2 into I. So I is 3.62. 3.62 into root 2 is nothing but 5.11 amps. This is Im. Now it is time to calculate the time equation for voltage V of t. We know V of t is nothing but Vm sin omega t, and I of t is nothing but Im sin omega t plus pi by 2. So it is leading in this pure capacitor. It is leading exactly by 90 degrees. So 5.11 Im into sin omega 014 omega t plus pi by 2. So in this lecture we have seen the resistor, pure resistor, and pure inductor, pure capacitor. So behavior of all the three parameters when connected to AC supply. Okay. So V equal to Vm sin omega t and I equal to Im sin omega t. So in pure resistor, these two are in same phase, and there is no any phase difference between the voltage and current in a pure resistor. The power factor also unity for pure resistor. Power factor is nothing but cosine of the phase angle difference between supply voltage and current. So in this, the phase angle, there is no phase difference. So phi equal to 0 and cos phi equal to unity. So in a pure resistor, the power factor is unity. And like inductive loads, so inductive means an inductor. So for an inductor, for a pure inductor, the current and voltage relationship between the voltage and current in inductor are the current exactly lags the supply voltage by 90 degrees, and in this case the voltage leads the current by 90 degrees. Here the voltage leads or current lags by exactly 90 degrees. In this, the power factor also, for inductors, the power factor always lags the supply voltage. For a pure capacitor, pure inductor, it is exactly 90 and somewhat less than non-pure capacitor. And inductive reactance will comes into the picture in case of inductor, and it is also like a resistance. This is the reactance. Units are volts. And coming to the pure capacitor, the voltage and current relationships are exactly, they have 90 degrees difference in a pure capacitance. Here voltage lags the current or current leads the voltage by exactly 90 degrees. So here capacitor reactance comes into the picture. The capacitor reactance is units are ohms, and XL equal to 2 pi FL and X equal to 1 by 2 pi FC, or XL equal to omega L and X equal to 1 by omega C. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.